So, hello again, everyone. Good morning. Welcome to our webinar series offered by the Balkan-Med Innova Project Web School. My name is Alexandros Galanidis. I am an environmentalist. I hold a PhD in ecology. Currently, I'm working as a researcher at the University of the Aegean in Greece, and I'm also an adult educator concerning environmental issues. Today's webinar is entitled Environmental Costs of Energy Use. And if you are all set, I will start with the outline of the presentation. So, in this webinar, we're going to discuss about the environmental consequences, the environmental costs of our fossil fuels-based energy system. You all know that every human activity, each one activity, despite its scale and quality, has a smaller or bigger impact on the natural environment. And as energy usage is perhaps the most fundamental aspect for human survival and progress, it's obvious that we expect major negative consequences to occur, particularly since our current energy paradigm is found to be one of the most unsustainable energy systems throughout history. This energy paradigm of burning fossil fuels. In this webinar, I will start in the first sections, section by talking about the most famous and severe environmental issue of our time, the most severe environmental problem of our time, which is, of course, global warming, and specifically its greenhouse effect component, with its huge contribution to climate change. Continuing in this mode, I will, during the second sections, I will shortly comment the carbon footprint concept and its shares, and I will try to present to you the main proposed strategies so far to cope climate change. So I will briefly talk about neutral, zero, and negative emission goals. In the last section, in the third section, I will address a very important issue regarding environmental cost of energy use. How can we conserve energy? What is energy efficiency, and which approach should we follow when we try to save energy and reduce the impacts of its use? So, to get started, let's look at the first section and discuss about global warming and climate change. Which is the base? Let me start with a question. Which is the base of global energy flows? Of course, it's the sun. I will make the answer. I don't expect you to give me some answers. Unless you want, you can use the chat or your microphone. So the sun is the base of global energy flows. Sun is the ultimate source of energy in our solar system, and all energy in our planet derive initially from the sun. Sun's rays, in the form of electromagnetic radiation, travel huge distances. It is calculated that it is about 93 million miles. There are lots of songs with that title. So sun's electromagnetic radiation travel 93 million miles through empty space and finally arrive parallel, as you can see here, to Earth's surface. But due to the spherical or elliptical shape of the Earth, solar radiation has uneven effects on the planet. In the equator here, solar radiation is direct, okay, and thus it is more concentrated to smaller areas, while on the north or in the south, on the poles, it's oblique, so it is more diffused and with a larger area cover. This leads to have 2.5 times more energy in the equator, more comparing to the poles. So the annual energy magnitude in the equator is 2.5 times more than the amount of energy that arrives to the poles. So solar energy in this fascinating way is arriving on Earth's surface, and it is arriving in huge amounts. Solar energy that arrive on Earth's surface is about 170,000 terawatts per square meter per year. Okay, this is a massive number. This is a massive number, a massive amount of energy. It can fulfill our planet's energy demands by 10,000 times more with values for 2004. You can see here that the world energy use for 2004 was just, we can say just comparing to the sun, 16 terawatts, while annually sun is giving us this huge number of energy. Also, this amount of energy, it cannot be, of course, compared with any other known source of energy that we have on Earth. For example, compare this number, this figure, with the maximum of 6 terawatt per year that biomass can give us. Okay, here is the amount of biomass, of whole biomass on Earth, and the energy that the biomass can give us. It's 2 to 6 terawatts per year. Or compare this figure with the maximum of 70 terawatts per year that wind can give us. Wind can give us a lot of power. It is one of the most successful renewable energy sources, but its magnitude of 70 terawatts per year is nothing comparing to this. Or again, compare the total amount of 2,240 or even the 900 that petroleum and coal can give us. This is the total number. Okay, if we use all the petroleum that exists now on the planet, or all the coal that exists on the planet, we would get 900 terawatts per square meter. So in our solar system, an interesting detail is that while other planets are either boiling hot or extremely cold, Earth's surface has rather mild and stable temperature. Of course, we have the desert temperature and the Antarctica temperatures, but these again are nothing against the total iced planets, or the surface of Mars, for example, which is actually on fire. Why is this happening? Why Earth is experiencing this rather mild and stable temperatures? Because our planet is experiencing, as we say, little net energy gain or loss. What is this little net energy gain and loss? It is another way to describe the equilibrium between the incoming radiation that reaches Earth from the sun and the outgoing radiation that flows from Earth back to space. That equilibrium, that balance between the incoming and outgoing solar radiation is also called Earth's energy budget. Let's take a closer look to this phenomenon and clarify how the net energy gain and loss of the Earth is almost zero, as you can see here. Okay, this figure. You can see that about 30% of sun insolation. Insolation is how we call sun's electromagnetic radiation. So about 30% of sun's isolation is immediately is reflected to space. Okay, either immediately by clouds and atmosphere, which contains tiny atmospheric molecules called aerosols, or this is the 1%, the one part of the reflected insolation, or indirectly after reaching the surface. So this is the solar radiation. One part, one fragment is immediately reflected by clouds and atmosphere. So it's about 22%. And another fragment about is absorbed, is reflected after hitting the surface. That is about 70%. Another part of insolation, about the 23% of the total radiation, is absorbed by atmosphere before reaching the surface. So 23% of the insolation doesn't get to the surface because it is absorbed this time and not reflected by atmosphere and its clouds. The largest fragment, the 48%, almost half of the insolation, is finally absorbed from the Earth's surface. And what we call, what we're meaning when we say Earth surface, it's of course the land, the ground, it's the oceans, it's the lakes, the rivers, and also it's the snow and ice areas of the planet. So half of the sun's insolation is absorbed by Earth surface. And what is this? This is a big amount of energy. What is that fragment cause after its absorptions? After its absorptions, it stays on Earth system. Earth system is what the whole planet is about, and it circulates in this Earth system. And what is causing during this circulation? It warms the land, the oceans, the lakes, everything. It warms the planet. That fragment is the energy that control our planet's climate. It's the energy that creates the oceanic currents, the energy that creates, that blow the winds on the planet. It causes the evaporation of water from the various water bodies, and in generally it drives the global water cycle. It is the energy that we feel as heat, as it is emitted from the surface. It is the energy that we and other animals are feeling as heat. It's the energy that finally make this planet a suitable place for living. Of course, as you know, from the first law of energy, from the first thermodynamic law, energy cannot be created or destroyed, but it can only change forms. While making all these great things that I just mentioned before, a part of the absorbed solar radiation that Earth's surface has is transformed to heat. Okay, it's changed its form, and it's transformed to heat. It takes another wavelength. It's now infrared radiation, and as infrared radiation move back through space. So a part of the solar radiation absorbed by the Earth's surface transformed to infrared radiation, and then tries to go back to space. Some of this heat is absorbed again by clouds, okay, here, and especially by various atmospheric gases, and then re-emitted downwards. So it's not an immediately in an immediate procedure, but it has up and downs, until all this radiation finally escape to space. These gases, these atmospheric gases that absorbed part of the re-emitted heat from the Earth's surface, that captivate a part of solar energy radiated by Earth in the form of heat, are called greenhouse gases. What are these greenhouse gases? Most of the greenhouse gases are naturally occurring, but they are also emitted as a result of industrial processes and other human activities. Other greenhouse gases are synthetic. They are strictly man-made chemicals. They are not occur in nature and usually are present in low abundances in the atmosphere, but they are more drastic most of the times. The main greenhouse gas is, of course, the most famous is, of course, CO2, the carbon dioxide. It consists 82% of the total greenhouse gases mix. It can move into and out of the Earth through the carbon cycle. Other greenhouse gases are methane with 9%. Methane is remain in the air for shorter periods of time than CO2. It's more kinetic. It's a more drastic gas, but it can trap more heat comparing to carbon dioxide. Another important greenhouse gas is nitrous oxide. It can remain in the atmosphere for about 1 molecule of nitrous oxide can remain in the atmosphere for 120 years. Okay, and it's even more drastic than methane and carbon dioxide. And finally, we have a big family of gases, the fluorinated gases, the F gases, as we say, that consists of 3% of the greenhouse gases mix, and they are man-made chemicals, synthetic chemicals that are more drastic than CO2, but we have them, thankfully, in less concentrations. So as these gases, the greenhouse gases, are trapping the heat that is re-radiated from the Earth's surface as heat, they work as a blanket above the planet, a blanket that warms the atmosphere and the surface of the Earth. This is a natural process that exists for millions of years now, a natural process with crucial importance for the survival and evolution of life on the planet, and it's called the greenhouse effect. The greenhouse effect, I say again, is a natural, beneficial phenomenon. It's the mechanism that keeps Earth at a habitable temperature, and without it, the planet would be too cold to support most of the known forms of life. So you see here again, sun isolation hits the Earth, the surface is absorbing a part of it and then re-radiated back to the atmosphere, and these greenhouse gases are captured a part of the heat and warm the planet and give us these habitable temperatures that we all still enjoy. Let's see this phenomenon in more details. You remember what I've said before about the Earth's energy budget. Actually, in simple words, what gets in, it gets out. So it's an equilibrium. So what would happen if Earth system changes and some imbalance occur in its energy budget? Take a look at this graph. On the left side, here, greenhouse effect with normal CO2 concentrations. We have an illustration of the beneficial natural greenhouse phenomenon. You can see here this reddish zone above the Earth. This is the zone of the greenhouse gases that trap part of the re-radiated heat from the surface and re-emit it back to the surface and to the atmosphere, and guarantees for millions of years now that Earth is a planet that we can live on. And here we have less heat with the normal CO2, less heat is trapped in atmosphere and more heat can finally escape into space. On the right side, on the other side of this graph, you see the altered greenhouse effect. The greenhouse effect with rampant CO2, which is rather than beneficial, is, as we say, one of the biggest environmental problem of our times. You can see here that this reddish atmospheric gases zone is much thicker, meaning that the greenhouse gases of the atmosphere are increased and found in much higher concentrations. So this is leading to less heat escape finally to the outer space and more heat trapped in atmosphere. This zone is thicker, these greenhouse gases are more effective, and they can trap more heat that re-radiated from the Earth's surface. In situations like this, where we are facing with such big changes in Earth's energy equilibrium, what will happen? The Earth system, will try to restore its energy balance. And at this point, of course, when we are talking about energy, we are talking about energy in the form of heat. So the effect would be on the Earth's temperature. Earth's temperatures will eventually increase or decrease in order to restore its energy budget. If the amount of energy radiating back into space is decreased, like as is this our situation, even by a very small amount, this can lead to warming. This is the case with the altered greenhouse effect. It gets our planet warmer and warmer. So who could have the strength to cause such changes to the Earth system? Notice that we're not talking about small-scale changes that could happen on a forest or on a lake or on a river. We're talking about the Earth system. This is the whole planet with its atmosphere, with its waters, with everything. It's a big, huge system. Who could have the strength to cause such changes to a huge system like that? First of all, it could be the system itself, the Earth itself, and it has done it before by large-scale natural phenomena such as volcano explosions or other natural phenomena or like meteorite falls. But of course, we haven't seen such phenomena since many years now. Next, we could suspect the modern industrialized human societies, some specific anthropogenic activities that could have the power to do so. Our energy system uses fossil fuels to get going. The energy that we get, the most part of it, is from fossil fuels. We burn fossil fuels to get energy. And in this fossil fuel economy that we're living, that emits greenhouse gases to the atmosphere, it's where we should search for the suspect of these changes in the Earth system. The greenhouse gases are a byproduct of the burning of fossil fuels, a burning that we need for our energy demands. So, which economy and social sectors are responsible for that? Where do greenhouse gas emissions come from. First of all, it's electricity and heat. Okay, electricity and heat, along with transportations here, as you see. So these two sectors, electricity and heat and transportations, account for about 40% of greenhouse gases emissions. Other important sectors are agriculture, with the fertilizers industry, which is a very big industry, and of course with the livestock emissions. So agriculture, along with other practices such as, for example, deforestation and several other land use changes, are credited for about 20% of carbon emissions. Industry in general, with the exceptions of the factories, the industry that is using for producing electricity. So industry have also a big share, both in terms of direct emissions, okay, see here the smoke, but also in terms of the produced waste that they have. There are also other sectors such as the food waste, the food that we don't use, or the constructions. And so the main sectors are electricity, heat, transportations, and agriculture, and of course, industry. You can see that I cannot say one or two sectors as the main sectors, because none of the economy sectors actually alone, none of the economy sectors alone can be blamed for a huge share of greenhouse gas emissions. So in order to address the climate change, we have to see the whole aspect of our economy. Addressing climate change is a very difficult task, though, as we must act almost in every aspect of our modern life, and each piece of these sectors requires attention, different strategies, special measures, and special efforts. Let's move on. During most of the current interglacial period, this is the periods between ice ages. So we live in a period like that. The last glacial period, the last ice age was 12,000 years ago. So during most of these interglacial periods, greenhouse gases concentrations were natural greenhouse gases were relatively stable. After the Industrial Revolution, and especially over the last century, human activities, anthropogenic activities, are increasing atmospheric concentrations of both natural and synthetic greenhouse gases. You can see in this graph the concentrations of three main greenhouse gases: carbon dioxide, methane, and nitrous oxide. For centuries, okay, from 1000, their levels, for 10 centuries now, their levels were stable, okay, and rather low. So we had no big fluctuations in the concentrations of all these three gases. But as we go through time and reach the post-industrial epoch, and especially after the first industrial revolution, which is the epoch that we start using coal, and especially, of course, in the last century, when coal and the other fossil fuels, oil and natural gas, were dominating the energy mix, these concentrations of these main three greenhouse gases were rapidly increased. The consequences of these changes in the concentrations of the greenhouse gases are difficult to predict. but several signs and very complex. It's a very complex procedure to predict, but we already have several signs. Several signs are already here. In the next few slides, I'm going to show you a few of these signs. Let's start with this graph where we have global temperature and carbon dioxide concentrations. So CO2 is the main greenhouse gas. Carbon dioxide is a naturally present gas, and it is a part of the Earth's carbon cycle, a very important nutrient cycle. It is also the primary greenhouse gas emitted through human activities. We know from data reconstructed from ice core samples, that before the Industrial Revolution, about 200 years ago, CO2 concentrations fluctuate between 180 parts per million during ice ages and 280 parts per million during interglacial warm periods. Since the Industrial Revolution, though, and check this orange line, we are from the end of the 17th century, so we are in the Industrial Revolution here, and this orange line and is the fluctuations of the carbon dioxide concentrations. Since the Industrial Revolution, the amount of CO2 is increasing 100 times faster than the increase when the last ice age ended. Indeed, in 2019, we measure the highest level in at least the last 2 million years. That was about over 400 ppm, parts per million. Along with the carbon dioxide, as we have explained due to the greenhouse effect, along with CO2 comes also temperature, okay? This yellow line. See here that yellow line that goes in parallel, that increase in parallel with CO2 concentrations. And the planet's average surface temperature has risen about 1 degree Celsius in the late 19th century, but most of this warming occurred in the past 35 years, with the warmest year of all so far to be the year 2016. Please notice that even if we now, at this moment, stop immediately all greenhouse gas emissions, the current CO2 concentrations will stay in the atmosphere for 1,000 years of more. It is not destroyed very easily. It can stay. It has this ability to remain to the atmosphere. So this is again a big problem concerning the efforts to cope climate change effect. So another example, another graph of this global warming and climate change science. You know that the temperature, of course, controls in a way the global water cycle. We have measured already, we have numbers of it, that the temperature of the deep oceans have been warmed up by 0.1 degrees of Celsius since the 70s, okay, since the last 50 years. The rate, and okay, perhaps this is, it seems that a very small number, 0.1, but remember that deep oceans and the oceans in general are a huge amount of water, okay, and in order to get this huge amount of water warmer, you need a lot of energy, and that energy eventually or unfortunately is staying on the Earth system instead of getting out to space due to the greenhouse effect. Another interesting number is that the rate of ice mass loss in Antarctica has been tripled in the last decade. So in the last 10 years, we have three times more ice mass losses in Antarctica. Arctic sea ice again has declined both in extent and thickness during the last decades. All these have caused a global mean sea level to rise by 20 centimeters in the last century. You can see here the graph. This is again the post-industrial revolution epoch, and you see the mean sea level that is rising, and it's about this increase about 20 centimeters, and even more in the last years. You can see here. Another interesting fact is that Earth temperature controls the water cycle, but it also controls the weather somehow. Extreme weather events such as heat waves, floods, or droughts are more common and severe since the 1950s. This graph is again for much more years. It shows data from the United States of America, and you can see that extreme precipitation, extreme temperature, extreme tropic phenomena, cyclones are getting more and more common in the last 100 years. So such changes would have effects on ecosystems, of course, and on the plants and the animals that these ecosystems are hosting. Shifts in plant and animals ranges, as well as changes in trees' phenologies, which is the time that they are blooming, the time that they are setting fruits. Has been already observed. We have seen these signs already, especially with plants. We can see here a graph of the pressures that global warming is applying on several butterfly with the red and birds with the green species. These species are trying to change their native ranges. They try to change the natural habitats that they use to occur. They try to find new places to live in order to avoid higher temperatures, droughts, or decreases in their food availability due to climate change. And what exactly are they trying to do? They are migrating in northern areas from the south to the north, to the north that has still lower temperatures. So they migrate to northern areas that they were not fit enough to live before, but perhaps now with the rise of the temperatures, they can be successful to do so. So several animal and plant species. It's very obvious this with birds and butterflies. They become in a way climate change refugees, climate change migrants, the situations that of course we know for several human populations. Now, before, we had this, I have planned this short video for these slides, but I have this problem. So we will move on to the second part of the presentations, which will look at the various strategies that have been developed to address global warming and climate change. We have talked already about the main sources of greenhouse gases emissions already. So we have to admit, though, that nearly every human activity releases carbon. Traveling either by car, by train, by airplane, heating our houses, our schools, our hospitals, consuming consuming food or clothes or electrical devices, all these activities are directly or indirectly contributing carbon to the atmosphere. This contribution reflects the amount of greenhouse gases that are produced to support human activities, and it is what we call carbon footprint. A carbon footprint includes all the major six Kyoto Protocol greenhouse gases, which are the carbon dioxide, of course, the methane, the nitrous oxide, the big family of other three gases from the big fluorinated gases. For simplicity and uniformity reasons, when we are talking about carbon dioxide, we are referring to all these six greenhouse gases, but we express its value in equivalent tons of CO2. In a given time frame, usually a year, we can calculate carbon footprint in various scales, from individuals to households, and from companies to countries or to the entire world. The magnitude of the contribution depends on various factors. So our carbon, the magnitude of our carbon footprint depends, for example, from the fuel on the fuel consumption of the vehicles that we are using, of the type, from the type of our heating source, from the packaging that the goods we buy have, from the distance our food is coming from, or if we either cook food or eat it raw. So, in other words, we can increase or decrease our carbon footprint with our everyday choices, with the policies we support or demand, and with the production mode we follow. So it is not only an individual level decision, but it's also a social one. Here in this graph, you can see, for example, the carbon footprint for different means of transportation. These values are the grams of CO2 that are emitted in order one person to travel 1 kilometer. Notice the huge differences between getting along by foot, by walking, or by bicycle, where we have almost zero carbon footprint. This is 1.5 grams of CO2 or 0.5 grams of CO2, and compare these figures with the use of an average old technology car that needs 10 times more to get one person 1 kilometer away. Or notice the difference between using a bus or using a tram or a train, and using our own private, even modern electric cars. Or check here the differences in another sector, the differences in the type of food we consume. See, for example, that for a kilo of tomatoes, about 1 kilo of CO2 will be emitted. Contrary, for a kilo of lamb meat, we emit almost 40 times more. Without that food, that meat, necessarily to be 40 times more nutritious or healthy in such a scale. As most of the things that are related to the environment, carbon footprint has also social and political aspects. There are huge inequalities on the carbon emissions between states, inequalities that are not due to their population size, but rather due to their economies size. See, for example, here we have this graph. The outer circle is the share of each country has to the world's carbon footprint, and the internal circle is the share each country has on the world's population. See, for example, that the United States of America has 4.5% share of the world population, so it hosts the 5% of the world population, and it has almost 16% share of the total global carbon emissions. While India, for example, with the 18% of the world population, has less than half of this share. Or check other numbers. For example, China, it has a huge world population share and also a huge carbon footprint share that is increasing more and more every year. So let's move now to the several emission strategies that are developing in order to cope the impacts of carbon of global warming, in order to cope the environmental cost of our energy use. It's basically these three strategies. They can have different meanings depending on the level that you are study them, but they are more or less the carbon neutral strategy, the zero carbon strategy, and the negative emissions strategy. What is the carbon neutral strategy? What we mean by being carbon neutral? This is reducing emissions where possible and balancing for the remainder by investing in carbon reduction projects in order to achieve net zero carbon emissions. You can see here that, of course, we have emissions. The first thing we try to do is decrease our emissions, but unfortunately, there will be remaining emissions that we will try to offset by producing clean energy in order to algebraically to have zero emissions. The key word here is net zero carbon emissions, as whatever we do, we must capture or offset as much carbon as we have produced by doing that action. For example, an office building with solar panels that sends renewable energy to the electrical power grid equal to the energy that these offices are taking from that grid. Carbon offsetting, this part here, is a process by which organizations and individuals balancing in the way their carbon footprints by funding emission reductions project elsewhere, somewhere else, which can offset their own activities, and finally they can become carbon neutral. So here's the video. Let's go to the next strategy, carbon emission strategy, which is the zero carbon. This is not an agreed scientific term. It's more a wish, a hypothetical concept. When we are talking about zero carbon, we are referring to net zero CO2 emissions totally without offsetting them. We are describing a case where no carbon, no greenhouse gases is emitted at all. So we don't have to offset any excess carbon. For example, That could be referred to a household that it's off-grid, to a household that it's on a forest, for example, a household that it's running entirely on renewable resources and use zero fossil fuels. But again, this is more like a wish, a hypothetical concept. It's something that we would like to achieve, something that we are going towards. The next concept, the next strategy is the negative emission. It is also known as carbon dioxide removal. It refers to some contagious technologies with the objective actually to take out, to remove CO2 from the atmosphere. How can that be done? First of all, it can be done naturally by some afforestation or reforestation projects that we are trying to create more carbon sinks, or through geoengineering, which is a new section of engineering that uses bioenergy, carbon capture and storage techniques that are about capturing or direct suck CO2 from the atmosphere and store it underground. This is a very contagious technologies that are not welcome from the majority of the scientific community because there are lots of risk when you are store huge amounts of CO2 underground in rock foundations. This could make huge differences, could produce huge differences in the underground waters, or cause earthquakes, and it's not something that could be environmental friendly, at least for the most of the people who are dealing with the environment. So let's move, as we cannot see the video, let's move on to the third and the final section of this webinar, which will deal about energy efficiency and conservation. Anyhow, in any way, the extent of climate change effects to specific parts of the world and to individual regions around the world will vary over time and will depend on the ability, on the potential of different societal and environmental systems to mitigate or adapt to that change, like animals, like plants. Also, our societal systems have to adapt to these changes. There are different policies and that could lead us to different climate, depending on political decisions and on measures to mitigate greenhouse gases. We are expecting different average global temperature increases in the future. That's why we have different scenarios. For example, this is a projection from 2000 for the next 100 years. With the green, it's the temperatures that we are expecting if we are follow the current policies. So if we are leave the things as they are now, we're expecting in 100 years to have 3 to 4, maximum 3.7 degrees Celsius higher temperatures. If we quit even these little efforts that were made to cope climate change, we would expect much more increase in the temperature, about 5%. So in 100 years, we would have a planet that would be for 5 degrees of Celsius warmer. So there are different scenarios. These scenarios are referring to CO2 emissions cuts. So the most restrictive one, if we follow the most restrictive one, we would again have a rise in the temperature, but only by 1.5 degrees of Celsius. A kind of policies, kind of decisions that we have to make in order to cope climate change and not have 5 degrees of temperature rise in the next 100 years. It's to conserve energy. Energy conservation, it's a very simple, at least at the beginning, decision and practice of using less energy. So there are different concepts, there are different practices that we can follow in our houses to use, to conserve energy, to use less energy. Energy conservation is focusing on the lifestyle model people are following, and they can adjust. Energy conservation is asking from us to adjust our personal behaviors and our personal habits. A change in our habits, to be successful for this change, we have to change some cues and create new routines that will eventually lead to a new reward. For example, if we are feeling cold inside our apartments during winter, our common routine is to get the heater up. Okay. Another routine would be to get a jacket on us or a blanket. I don't know. So this would create a new routine because without using more energy, we will have the same result. We will be warm again. So this would be the new reward would be that we will feel warm again and we would use less energy, we would emit less greenhouse gases. Another very interesting concept is, along with the energy conservation, is energy efficiency. Energy efficiency refers to the amount. It's not about using less energy, but it's about using less energy to provide the same service. So it's the amount of useful energy output relative to the energy input, how much energy we get comparing to the energy we put on a system. It's about how effective an energy system is, how effectively can convert energy from one form to another. It focuses not on lifestyle and habits, but more on the equipment and the machineries that were used. So energy efficiency involves technology, and this technology must waste less energy in the form of non-useful byproduct in order to be efficiency. And the main non-useful byproduct of the technology we use, of the machinery that we use, is heat, of course, and noise. For instance, an example of energy efficiency is using light emitting diode lamps that use less energy to produce the same amount of light. So if we replaced this lamp, or if we replaced a single pane window with an energy efficient one, with a double or triple window, that would prevent heat losses from our house, and therefore we would have the same temperature in our house, but using less energy for it. Here are some numbers about energy efficiency of lamps, of the different types of lamps. You can see that here to get the same results 1600 lumens. With the traditional lamps, you should use 100 watts, but with LED lamps, you can use just 19. This is also a matter of money. You need $2.50 per year instead of 13. So both energy efficiency and conservation can save energy. So they can save greenhouse gas emissions, they can save carbon in the atmosphere, but they also can save money. With efficiency, we have the same output for lesser energy, and with conservation, we're just reducing the consumption of energy or stop the waste of it in various byproducts. Still, besides this energy efficiency and energy conservation efforts, or in other words, if we are trying to follow these practices without thinking about what are we doing, we can end up with an energy paradox because the components of, as we say, the development blocks are the whole systems of technology, the systems of infrastructure, energy sources, institutions. It's the whole system that drive economic growth. This system can be at the same time or in different times both energy saving or energy expanding. And you all know that at least our system in capitalism, it has this tension of being expanding in various aspects. So what is this energy paradox? As energy efficiency improvements in technology is reducing the energy cost of production or the energy cost of using a technology, they can make this technology more cheap, more affordable. So, and by doing so, some people would be keen to use it more often comparing to the past. So we're expecting huge expansions in the use of energy. For example, check this graph about the energy paradox, which is an unplanned consequence of energy efficiency efforts, because we have lower petrol bills. So with lower petrol bills, we can go, for example, holidays in Spain that we would not going in other occasions. So we would take an airplane and we will use more energy. Or with lower petrol bills, we would have lower running costs for a new technology car that will lead us to drive this car more because we can drive more kilometers with the same amount of petrol. So finally, we would get more energy. So maybe we are more efficient. Maybe the technologies that we are using is more efficient and use less energy to give us the same amount of pleasure or need. But by this paradox, we can end up to have a net increase in our energy demand. So what can we do to avoid this energy paradox, or what can we do when we are concerning about the environmental costs of energy use, as we should do in this epoch of global warming and climate change? First of all, we have to start from the base. Okay, we have to use an hierarchical approach. And what is the base? The base is to cut off the quantity we are using, the quantity of energy. So spend less energy. The second is use improved energy. use efficient energy and improve the quality of the machineries that we are using. The third step is to clean the source, so to produce better, avoid fossil fuels, and introduce renewable energy sources. You can see these in that graph. The first thing we should do is energy conservation. So spend less energy. The second is use better energy, be energy efficient. And the third thing is using renewable energy. We cannot go ahead for using windmills or using solar panels if we cannot cut the consuming of the energy we use. So the basic thing is energy consuming. Energy conservation must be at the base of our approach when we're talking about environmental costs of energy use. So I suppose that will be all for today's webinar. Thank you for attending. Sorry for the problem with the videos. Hope to see you in perhaps a next webinar. If you have any comment or any question, please use your microphone or your chat. I would give you a few minutes. So thank you again for attending this webinar. Take care. Ciao.